All right. So we're still talking about friction. Today we're going to do more problems and less talking probably than we did on Wednesday. I know that's hard to believe.
But it was so nice to learn about bearings.
Yeah, but you got to learn about bearings on Wednesday. So before we start though, I want to recommend a book to you. It's called Blink, and it's by Malcolm Gladwell. You read that book?
Yeah.
Did you like it?
Is it about engineering? Remember this part with people holding chicks?
People holding what?
Like little chicks. And then, I don't know if it was this one, but they were training them to figure out which ones were like boys and girls. Like female chicks.
Yeah.
And but they couldn't, like it wasn't something you could consciously tell, but
Yep.
over time they just knew how to do it.
Yep. Yeah. So this book is about it's about our subconscious and how we make quick, snap decisions. And the parts I found most interesting about it were on bias and prejudice. And so I'd really encourage you to read it. Or listen to it. I listened to it. You can check it out from my library for free and listen to it as an audiobook. You'll be smarter if you do. So I'd still encourage you to read it even if you took psychology. Yeah. So. All right, so friction. What did we learn on Wednesday? Okay, it looks like Brendan didn't learn anything. Normal force is off center, yeah. So if we have a box and we're going to pull on that box with some force, we know that the box has some weight and that the force of friction always opposes impending motion, right? So we don't know that the box is necessarily going to move, but we know that the force of friction will counteract that impending motion. And that the combination of this P and the force of friction causes a clockwise couple moment. To counteract that then, our normal has to not be right underneath the weight. And that this distance here, which we could call x, that lever arm, has to be able to counteract this moment. If not, what happens? Yeah, if not, it's going to tip. Okay? So we're going to look at a bunch of problems today around that. What else did we learn about friction? On a wheel, it's not going in the intuitive correct direction? Yeah, so if we have ground and we have a misshapen wheel, right? This will not be very comfortable, but it depends on whether the wheel is braking or accelerating. So we think, let's say the wheel is accelerating to the right, okay? Then the force of friction on this, we would think, well, it should be going backwards. It's not. It's actually the force of friction on the wheel is going forwards. Because you have to think that the wheel is trying to spin this way very hard. So impending motion would be the wheel sliding past it. Now what if the wheel is traveling, that one's better. The wheel is still traveling this way, but we're applying the brakes. Now what direction is the force of friction going? Now it's going back this way because it's slowing whatever the wheel is tied to down. And the reason that's happening is because this guy is exerting a moment this way. Okay. All right, so let's take a look at an example problem involving friction. Here's a 100-pound box. I'm going to tell you that mu static is 0.4 and mu kinetic is 0.3. And we're going to pull on this box right at the top. And we're going to pull with a force of 35 pounds. And I'd like you to find out what the force of friction is. And I'll give you some dimensions for the box, because those are, turns out in this problem, are kind of important. Okay? So, do we have an equation for the force of friction? What's the equation? Like that? Is that true in this case? It is. What mu is this? Huh? I don't know. I haven't told you. That is pretty important. So how can we, so the question is it moving? And I'm saying I haven't told you. So how do we figure it out? How do we decide if it's moving or not? Mu is given. So why don't we try equations of equilibrium, right? So our equations of equilibrium, we could say that the sum of the forces in the x has to be equal to 0, right? Okay. What are our forces in the x direction? Maybe we should start actually by drawing a free body diagram, because we don't have a complete free body diagram yet, do we? No, so we're going to be kind of chasing our tails. Maybe I'll just use this one here. What forces am I missing? Friction and a normal. Okay? Which direction will friction go, Brendan? Opposite of the 35. Why do you know that? Say that again, Jason? It would definitely be moving if we had the friction going in the other direction, right? It'd be accelerating that. That'd be kind of cool. Nice linear accelerator there. Yeah, so it's opposing impending motion. So that's the phrase you kind of want to think about in your head, is impending motion. What is about to happen? Where is sliding about to happen? And this block is about to slide to the right if we didn't have, if we didn't have force of friction on it, what would happen? Well, the block would accelerate to the right. So what does friction do? It counteracts that. Okay? All right? Leon, I think you had another force we're missing? The normal. Okay? So we don't really know where the normal is, but we know that it acts normal to the surface. So now, I think we have all of our forces here, so let's go back to our equations of equilibrium. What do we have acting in the x? What else? Minus the force of friction equals 0. Okay? Now, force of friction, do we know that this is true? Is this always the case? Is the force of friction always equal to mu static times normal? It is. Sweet. All right, so let's figure out what the normal is. Sum of the forces in the y equals 0. Okay, what's happening in the y? Negative 100 plus n equals 0. Okay? Looks to me like the normal force is 100 pounds. Okay? Now, we've stated that the force of friction is always equal to mu normal times 100, okay? So that means I can say, oh, my force of friction is mu static 0.4 times 100. So the force of friction is 40 pounds. Hold on a second. If I stick 40 pounds back into this, what does it tell me? It tells me that the block is moving, exactly right. Friction is somehow accelerating the block to the left with 5 pounds of force. Does friction ever accelerate anything? That's like antithetical to how it works, right? So is this always true? This is not always true. Okay? When is this true? There are two cases when this is true. When it's not moving? Well, it's not moving right now. Is this true? Huh? Yeah, you have to figure out if it's moving or not. We haven't figured that out yet. I'm going to tell you the two cases when this equation is true. The first one, when sliding is happening. Right? So if we're sliding, we know we can use mu kinetic in this equation, and that will tell us the force of friction. The other case, when sliding is about to happen. All other times. So the question was, when is this not true? Every other time except these two, right? So this is actually never true. I'd like you to think about this equation this way. The force of friction is equal to mu times the normal. Never, except when you're sliding or when you're about to start sliding. So kind of throw this equation away, right? Because I think it's tempting for us to say, oh, we can calculate the force of friction. It's mu static times the normal. No, it's not. The force of friction is an unknown, except in two cases. One where you're sliding, and you can use mu kinetic. And the second, when you're about to start sliding. And that you have to pay attention to the problem, the wording of the problem, to see if that's true. Okay? So if we go back to this, I started by saying I'm going to make you determine if we're sliding or not. What is the maximum static friction we can have here? Maximum static friction, 40, right? So the maximum friction, force of friction max, is equal to 0.4 times 100. If we solve this, right, we can just solve this right here. What's the force of friction in this problem? Looks like it's 35 pounds. Okay. Is the 35 pounds less than the force of friction max? Yes, it is. Okay. So since 35 pounds is less than the maximum force of friction, that means we're not sliding. We haven't overcome static friction. So if the force of friction is less than the force of friction max, mu static has not been overcome, and the force of friction, all we know is that the force of friction is less than, right? Good question. Is the force of friction positive 35 or negative 35? So the variable here would be positive 35, right? It's going in the negative direction. So the magnitude of it would be a positive 35, in the negative direction because it's already pointing the right way. Exactly. Yep. Okay. Good question. All right. So the question was, do we assume that it starts from rest? Because it could be that it has already overcome static friction, right? And so then if we know that we're in case one up here and we have a sliding problem, then we know right off the bat that the force of friction, that's one of our special cases, and we can say, oh, if we're sliding, the force of friction is going to be equal to 0.3 times 100, which is going to be 30 pounds. Okay. If that's true then, and I stick that back in here, are we in static equilibrium? We're not. We're accelerating. So we're not in this class. So that is outside the realm of our understanding. Okay. All right, let me give you another one then.
Good question.
Yeah.
Why were dimensions important in the other problem?
Good question. So Daniel's asking, why were dimensions important in this problem? Why were the dimensions important? Brendan says they weren't. I say they are. Why? Because is this going to roll over or is it going to slide?
Well, that's not what we're looking for.
Fair point. So Brendan says we weren't looking for that.
So it's not important.
Neither is Brendan's grade, apparently.
Oh,
Okay. So to answer your question, Daniel, the reason they could be important is if I asked, instead of it, I asked what's the force of friction in this case. If instead I said, does the block move or not, right? We'd need to determine if it's going to tip over. Does that make sense? Okay. Okay. That's a 0.5, not a 0.6 for mu static.
Are dimensions important for this one?
No, because again, so the question is, are dimensions important on this one? And the answer is no, because again, I'm asking just what's the force of friction? So what's our free body diagram need? Yeah, friction and normal force. How can I tell if this thing is sliding or not? Hmm? If the so how do we want to say this? If the resultant force, how about if the applied force? Horizontal force is greater than the force of friction. Max. So no, we'd still be doing the problem. So if it was sliding, we could still do it. We would just know exactly what the if this is true. But that doesn't really matter because all we're asked to find is the force of the friction of the block. I'm not asking you to tell me where it is. Right? So the question is if this is greater than it, we can't tell. No, actually we can. So if the applied horizontal force is greater than FF max, what does that mean about the force of friction? Yeah, that means that the mu kinetic normal is the force of friction, right? If the applied horizontal force is greater than the maximum force of friction, then we can just automatically go to the force of friction is mu kinetic normal. How do we figure out if this is true, right? How do we put that into an equation? Yeah, it's what we've been doing all term, really, right? Some of the forces equal to 0. Looks like we'll have 30 cosine 30 minus the force of friction is equal to 0. Right? That's great that that's what you did. So you find that the force of friction is equal to what then, Brandon? 26? Oh, you didn't actually do it.
I wrote it.
You wrote it.
I didn't put it in my calculator.
It's 26? Okay. So the force of friction is 26 pounds in this case. Is that greater than the force of friction max? Well, we need to figure that out. The max force of friction, we need to do sum of the forces in the y equals 0. How many people said the max force of friction is 37.5 pounds? Anybody? Yeah, because that'd be 75 times 0.5. You have to find the normal, right? Because this is pulling up some, so the normal is less, right? So I have to actually do the equations of equilibrium and say that I have, in the y direction, I have 30 sine 30 minus 75 plus the normal equals 0. So what'd you find for the normal? 90? I don't think so. 60. I think you went the wrong way with the sign there, right? Probably. Yep. So 60 pounds. So if the normal is 60 pounds, then the force of friction max, right, is going to be 0.5, so mu static times 60 pounds, which is 30 pounds. Is 26 over 30? No. So this is indeed the force of friction. Okay? Let's keep doing these. Okay. Anyone get some numbers for me here? 70.5 pounds for the force of friction. Normal's what? Okay. No, this is a 20. Okay. So is this my force of friction? We have to check, right? What's the force of friction max? The force of friction max is going to be 0.2 times 126, which is 25.1 pounds. That's my maximum force of friction before what? Before it starts slipping, right? So can I ever get 70.5 out of this? No. Therefore, do my little three things. Therefore, we are moving. I don't know if I'm using that right, but. And if we're moving, so kind of the question we're asking is slipping happening? The answer is yes, it is. So, force of friction then is equal to 0.15 times the normal force of 126 pounds. Mm-hmm. In mathematical proof language? Mm-hmm. It's also like QED, right? Which is like Latin for I'm right. QED, it's like Latin for I'm right. It's not quid pro quo. Nope. Yeah. Good, you're qualified to be president then, because apparently you know what it is. Yep. Just saying. What's the force of friction then? 18.9 pounds. Okay. How you feel about these? Getting it okay? So far, so good?
So if it's greater than the force of the max, then you know it's slipping, and then that means our actual force of friction is the kinetic mu multiplied by the.
Yes. So what Liana is saying is that if the force of friction shows to be larger than the force of friction max, slipping is happening. So the force of friction is actually mu kinetic times the normal. Exactly right. Okay. So there's another kind of friction problem we need to be able to handle. And that's the impending motion problem. Do we only work with boxes? Is that what you said? No. You do not only work with boxes, but your homework is boxes. Okay. So now we're going to say we want to figure out if this box is moving or not. Typically, actually, the question would leave the 75 pounds as an unknown, and we'd say, what is the largest force we can pull on the box with before it starts to move, right? So this is an impending motion problem. We're trying to figure out how is this thing going to start moving first, okay? So what's our free body diagram look like for this guy? What am I missing? Okay, I'm missing a normal force and a force of friction. Okay. Now, let's do our normal equations of equilibrium. Sum of the forces in the x. Wow, that looks like a little cobra, doesn't it? See, it's like curled up, and then it's got giant fangs. It's like gonna bite the F. It does look like we're gonna play Hangman as well. It's Friday, everybody. All right, so what's happening in the x direction? 75 pounds minus the force of friction equals 0. So this says force of friction is equal to 75 pounds. Okay. How do we check to see if this is indeed true? Find the normal and see if this is less than F max, right? So we want to know, is the force of friction less than F max? Yeah, it sure doesn't look like it's going to be, does it? So let's sum the forces in the y direction and set that equal to 0. In the y, it looks like I'll have the normal minus 100. So the normal is equal to 100 pounds. So that means that F max is equal to 0.6 times 100, or 60 pounds. Is the force of friction less than 60 pounds? No. Okay, so what's that told us? The force of friction is not 75, and we're sliding, potentially. Maybe. We don't know. Okay, so we know that we've gone past the static friction, so we're going to have the force of friction, then we're in the case where what we found is greater than FF max, so then the force of friction drops to just be 0.5 times the normal, or 50 pounds. Okay? But we actually need to look at a third equation here. We need to sum the moments. There's a couple different ways you can do this, or a couple different locations you can sum the moments about. I'm going to suggest we sum them about a point in the middle at the bottom. Okay? I'll call that point B on here. Got to be equal to 0. So if I sum my moments about B, I'm going to tell you that this is some distance x away. I don't really know where the normal is. Okay. So what would my sum of the moments look like? Okay, normal times x, which we've already determined what the normal is, right? It's 100 pounds. Okay. What else causes a moment about B? 75, positive or negative? What's the lever arm? 1.75 feet. Okay. So if we solve this for x, what do we get? $1.31? 1.31 feet. So this is telling us that in order for this to be in static equilibrium, we need to put x equals 1.31 feet. So that means that the normal force needs to be pushing up on it about right here with 100 pounds. That's impossible, right? The furthest that this can go is right here, is half a foot. So what's going to happen? The box is going to tip over. Okay? Before we either, well, let's figure out what force that happens at. Right? So we're saying we're applying 75 pounds here. We've determined that, okay, we can't have that much force of friction, so we know motion's going to happen. And then we look at it, we sum the moments, and we say, hey, this thing's going to tip over. So let's figure out what force, at what force does this tip? Okay, so let's change the problem a little bit. Yeah, what applied force causes the box to tip over? So I'm just going to redraw it here. So the question is, wouldn't it be 75? The answer is no. It's going to tip before then. We just know that at 75, it's definitely tipping.
Oh, you're trying to find like the minimum.
So I'm going to leave this as P. Okay?
Yeah, you don't need that much space.
Wow.
Find the smallest force required for motion. What would the rest of our free body diagram look like? Force of friction.
Is there a force that would cause it to break the max friction and not tip?
So the question is there a force that would cause it to break the maximum force of friction and not tip? Not at this location. If I moved it down, you bet. Right? So if I move down my 75-pound force, we could still break the force of friction and not cause it to tip.
So wouldn't the answer for P be does not tip? Because it will never start moving without tipping?
No, because tipping is motion. Yeah. Yep. Okay. So probably the most direct path to solving this, right? Everything here, we know that the normal, if we look at this, we know the normal is 100 pounds. Right? We can sum the forces in the y direction if you want to do that. But we can jump straight to our summing our moments. And I'm still going to sum about the center here. That's how I like to do it. Some people like to sum about the corner. That makes it harder to put in terms of x, in my opinion, but whatever. I'm going to sum about b here. Okay? So summing about b eliminates the force of friction and eliminates the 100 pounds and leaves me with 100 times x minus p times 1.75 equals 0. Now it looks like I have two unknowns there, doesn't it? X and p. Okay? But I want to find the smallest force required for motion. So when it tips, where will my normal force be? Because we're saying this moves back and forth, right? Where would it be located? It'd be located right at the corner, right? That's the furthest I can get it away. So x then would actually be 0.5. So then I can see I have 50 is equal to p times 1.75, or p is equal to 27, 28, 28.6. Okay. So at p equal 28.6 pounds, we know that this thing will tip over. Let's check and see if it would slide before then. Brendan is shaking his head no, it's not going to slide before then. Right? Because if we go up, we found that the maximum F max was 60 pounds. Right? So we are still, static friction is still, we're less than that at 28.6. The force of friction would have to be 28.6. That's less than FF max, so we indeed would tip. Okay? I want you to work with the person next to you and find the required mu static so that the block tips before it slides. Okay? So I want this block to roll before it slides.
Quick question. For the normal, do we always assume it's to the right? Because it could be to the left and that would cause a different
So, good question. The question is, do we always assume that the normal is to the right? Because if it was to the left, it would cause a different moment. So, you need to assume that the normal moves in the direction that would counteract the moment that's caused by the applied force. Does that make sense? So far, it's always to the right because I've always put the load going to the right, which causes a moment that way. Yep.
still under the box, so that's cool.
Right, but that would mean it would slide because the distance outside the box. So I tried plugging in the known values that we do have, which is the force of friction. Calculated to be 40, the normal 60. So we just said, oh, that must be whack. Makes sense. I don't know where to go from here. Feels like we're doing well. Now, man. Alright. You onto something?
It doesn't matter what the new static is, it's always gonna be.
Because
It could be zero, it's
the
still
normal
like
would have to counteract it.
because the moment will always be push it out far enough.
Yeah, because the normal would have to counteract it.
Because we found that the distance for the normal force would be 1.66, 1.33 out the middle. So, and that doesn't bring in the force of friction.
Well, if we take.
All right.
If we calculate the force.
So far the vote I've heard is that it will always tip, right? What if there's no force of friction? If there's no force of friction, it's just going to go flying to the right, right?
So wouldn't it just be the 0.66 or whatever that it is?
The straw free body diagram. I haven't thought all the way through it to tell you whether you're right or not.
So the new static right now, the max is going to be 0.66.
Okay, so, but at 0.66 it would tip,
So I think
right?
less.
But we're asking, I want you to find the required mu static so that the block tips before it slides. So it's going to be less than 0.66. Let's find out how much. Okay. So the normal, you good with saying that it's 60 pounds? Just kind of by inspection. Okay. Then let's sum our moments. I'm going to do it about the middle again. Call it B. Okay. So the moments about B, it looks like I'll have my normal, 60 pounds. And if it's going to be tipping, that means it's going to be right out at the edge, right? So we know it'd be 60 pounds times 1 foot. For it to tip, then we're going to have minus 40 pounds times 2 feet. Well, snap-tastic, we know it's tipping if we get to this point, right? Because that doesn't equal 0, right? This equals, what's this equal, negative 20? So we know we're tipping if we get our full 40 pounds. But the problem is, right, so we're saying, what does this, how do I explain this? I made this problem a little bit more conceptually difficult than I wanted. At 40 pounds, this is saying that we're able to apply the full 40 pounds before motion occurs, right? I'm saying that that's not possible.
So why did you write 40 on the...
Yeah, why did I write this? You're right. The problem would have been much, much better. Let me change it. How about this? Let me change it and say P.
Okay, that would be a lot easier.
Okay. But still, find the required mu static so that the block tips before it slides, and I'm going to give you P there.
What if you solve, like, what if you put x for the normal distance, and then you solve for that? What is that giving you? Like, what does that represent?
If I put X here,
Yeah, and then you're like, well, we know what
That would tell me that the X is going to be, yeah, that it's way over here because X would no longer be on the block, right? But so what I'm looking for is I'm trying to make a hard problem here, which I think I'm succeeding at. And I want you to figure out what the mu static is, okay, so that it will tip before it slides. Okay, so if we know that P is up here, how does this change the problem? Well, we can say this is P, I guess, right? So let's figure out what load is that. Yeah, it looks like a P of 30, right? So we know that we need to pull with 30 pounds in order for it to just start tipping without it moving, right? If this guy is not moving and we pull with 30 pounds, we're just about to start tipping. Everybody understand that? Right? I don't see lots of understanding eyes. I see lots of, I'm tired and you botched this problem, so I'm not listening anymore eyes. Okay? All right? I kind of just described you? Yeah. The word my dad would use for that is glaked. You have a glaked look on your face. Glaked. Yeah, it is. Glacid. Let's look it up. Glaked.
Yeah, my phone.
Blades, kind of like blades. Glass or
This is a horrible dictionary. It's like all advertisements.
It didn't pop up. It tried to correct me to
Flaccid? That's what it tried to correct me to as well, and that is not the word we're looking for.
Are you sure that's a real word?
I'm sure. Oh man, I'm a little worried now. I've used it as a real word all my life, but maybe it's not a real word.
I think your dad was just making something up.
Maybe I'm spelling it wrong. C-A. Glacked in the Urban Dictionary is the guy got glacked by the drive-by. I'm pretty sure that's not it. All right, I'm gonna have to look it up later because this is taking too much time. Apparently, it's dubious whether this is a word or not. Okay. Back to our problem. Can you agree with me that we can determine that P has to be 30 pounds for it to tip? You look unsure. Let's do this. I'm going to draw a box right here. We have a 60-pound force here. We have some force P here. And we have a normal force there. And the normal force is equal to 60 pounds. Okay? We have a force of friction here. If I sum my forces about this point in the middle, what does P have to be equal to so the box doesn't tip? 30. Right? This is we're back to like chapter 3 or something like that. Okay? 30 pounds.
If P was less than 30, then the normal would just move somewhere else.
Yes, if P was less than 30, then the normal would move someplace else. But I'm saying we want this to stay in equilibrium. What does P have to be equal to in order for it to be in equilibrium given this? Okay, so we're agreeing that we need P equals 30 pounds. All right? So then what's the minimum mu static so that the block tips before it slides? If we know we need 30 pounds of friction and we have 60 pounds of normal force, we're saying our force of friction has to be equal to 30 pounds, which has to be equal to mu static times the normal, which would be mu static times 60, and it turns out mu static then is 0.5. Okay? So the problem with my problem is that I gave you a number here. Okay? You still could have done it technically.
Well, we would have had to change that number, which would have,
That would defeat
that
the
would change
problem.
the problem.
Yeah, so how would we change the problem if we can't change the problem?
It's like going
No,
on a
you still
test
could have
and-
done it.
It's like going on a test and changing the numbers and say, these numbers I like more.
They don't work, I'm gonna change.
Fair point. I see what you're saying. You can't just on a test cross out numbers and say, I don't like these, I'm going to do these different ones.
Yeah.
That won't go well for you. Okay?
Rewrite the problem for yourself.
All right. We only have 10 minutes left. Let me give you one that I'm sure is stellar.
Solvable?
Oh, boy.
Go over that word, solvable.
This has all I'm thinking about right now. Too much dilemmas. You can always keep right. I don't recommend it. That's what get down, take it down.
You too?
Yep. Oh my gosh.
Yeah, I asked her that line because I can't go. Apparently now she's not going, so you gotta do it.
Did you use all the clay yet?
No, there's still a little bit left, so we need to fix it.
I mean, is there enough to make candles?
Candles, yeah. There's like a good chunk left, just leave enough to do that.
I need to trim today too. I'll put it back. Put it back. I heard this conversation. I heard. It's for the box.
Hmm?
Spoilers. Oh my gosh. We're working on this. Let me get there first.
So the essence of the question, asking if it's gonna slide first or if it's gonna tip first?
Or if it moves at all.
Okay. So it's always asking which one first. If it moves.
Maybe you'd like it if I did this better. to essentially asking the same thing. At what force value of P does the block move? When it moves, does it tip or slip? So let's assume two types of movement. So let's say if it slides, what does the force of friction have to be overcome? Has to overcome force of friction max, right? Which would be equal to 0.6 times the normal. We have 100 pounds, so we know the normal is 100. So at 60 pounds, the block slides, or the force of friction is overcome. Okay? If it tips, then we need to put our forces on here. Say our normal's there, force of friction here. If we do that, here we actually, if we're solving the tipping problem, I suppose it does make sense to put where we're summing about right on that corner, because that eliminates the normal and the force of friction, right? So now I have some of the moments about the corner equals 0. I'll have 100 times 0.75 minus P times 2 equals 0. So 75 equals P times 2, where P is equal to 37.5 pounds. Which one's less, 60 or 37.5? Okay, so at 37.5 pounds, what happens? Box tips. Okay. All right. So your homework is posted. It's graded problem 8, I think. And it's a box on top of a box. Okay. And I think the boxes are like box A, box B. And I think some dude is pushing on it from the side. So what are all the different ways that you could have motion here? Okay, so you could tip the whole enchilada. You could tip B. You could slide B, or you could slide A and B. Okay? You could tip A and B. Yep. It'd be tricky, but I think you could do it. Okay? So, go ahead. If mu was, what's that? On the problem? Yes, the mu here is larger than the mu here. Okay, so you need, but the normal here, right, is is larger than the normal here. Right, so you needed to figure out, am I going to slide the whole thing, Am I going to slide B off of A, or am I going to tip the whole thing, or am I going to tip B off of A? Okay? That is due Monday. All right? Monday we'll do a little bit more friction-y stuff. We will have a quiz on friction. Then we'll get ready for Thanksgiving.